Hello there, and welcome to the Sleepy Science Channel. Tonight we'll be looking upward into that vast and beautiful expanse above us. Not into the stars, but into something even closer, something that touches us daily with its presence. We'll be exploring the clouds. Clouds are gentle architects of the sky, sculptors of weather, painters of light and shadow. They drift through the air with a quietude that seems almost conscious, as though they are traveling with purpose, with intention. And yet, there is no mind behind them, no direction but the wind, no goal but the simple physics of water and air meeting and transforming one another. For millennia, humans have gazed at clouds and wondered. We've seen castles in their shapes, faces in their formations, and meaning in their movements. Ancient peoples watched them to predict rain. Farmers studied them to time their planting. Poets wrote of them as messengers of emotion and change. Clouds have been muses for artists, subjects of scientific inquiry, and sources of both practical knowledge and pure imagination. But clouds are more than just objects of wonder. They are the engines of Earth's water cycle, the blankets that regulate our planet's temperature, the factories where water transforms from one state to another in an endless dance. They are the medium through which the sun and earth exchange energy, the collectors of minerals and dust, the deliverers of rain and snow. Without clouds, Earth would be a barren, lifeless sphere. With them, our world blooms with possibility. As you settle into this moment, letting your shoulders relax and your breath deepen, imagine yourself lying in a meadow on a gentle day. Above you, the sky stretches endlessly. Clouds drift past in slow, unhurried processions. There is nothing to do but watch, nothing to achieve but rest. The clouds ask nothing of you. They simply drift, simply exist, simply perform their ancient work while you breathe and observe. In this journey through the science and poetry of clouds, you'll discover why they move the way they do, how they form from nothing but air and water vapor, why they take their particular shapes, and how they have shaped human history and culture. You'll learn that the simplest-looking cloud is actually a complex phenomenon, a ballet of physics and chemistry and thermodynamics. And perhaps, in understanding clouds better, you'll find them even more beautiful than before. Every cloud is made of countless water droplets, so small they float on air. Look up at a cloud and what do you see? A white mass, soft and pillowy, seemingly solid enough that you might imagine lying upon it. But this is an illusion of distance and scale. In truth, a cloud is made of countless tiny water droplets, each one so small that millions could fit on the head of a pin. These droplets are so minuscule and so light that they remain suspended in the air, floating as easily as dust motes in a shaft of sunlight. How small are these droplets? A typical cloud droplet has a diameter of about 10 to 20 micrometers. To put this in perspective, a human hair is about 70 micrometers across. This means that a cloud droplet is roughly 1/3 to 1/2 the width of a human hair. And yet, despite their incredible smallness, billions upon billions of these droplets cluster together to form the clouds you see stretching across the sky. The reason these droplets don't fall is that they are so light and so small that the air currents pushing upward against them are strong enough to hold them aloft. The terminal velocity of such a tiny droplet, the speed at which it would fall through still air if gravity alone acted upon it, is incredibly slow, on the order of centimeters per second. And since air in the atmosphere is never still, since it's always moving and churning, these droplets remain suspended, held up by the wind's gentle pressure. This is one of the most elegant arrangements in nature. The droplets are small, enough to float on air. They cluster together in such vast numbers that they become visible to us from great distances. And yet, individually, each one is so tiny that it passes through our fingers if we try to catch a cloud, leaving us with nothing but a slight dampness on our skin. Clouds are almost entirely empty. Space estimates suggest that clouds are only about 0.03% liquid water and 99.97% air. And yet, when billions of these droplets cluster together, they become opaque, visible, substantial. To stand in a cloud is a surreal experience. Visibility drops to just a few meters. The cloud that looked so substantial from a distance dissolves into mist around you. You cannot see your hand in front of your face. And yet, you are breathing in the very substance of the cloud, drawing millions of water droplets into your lungs with each breath. The cloud, which seemed so tangible from afar, reveals itself to be nearly nothing but air and the faintest traces of liquid. This transformation from looking substantial to being nearly invisible when entered is one of the profound lessons clouds teach us about perception and reality. We think we see the cloud as it is, but what we see is an optical phenomenon, a trick of light and distance. The cloud itself remains indifferent to our observation, performing its work regardless of whether we understand it. Clouds form when water vapor condenses around microscopic particles of dust and salt. Water is everywhere on Earth. It evaporates from oceans and lakes, from soil and plants, from the very breath of animals. As the sun warms the surface, water transforms from liquid into vapor, becoming an invisible gas that rises into the atmosphere. This water vapor is weightless, transparent, utterly invisible to our eyes. But water vapor cannot simply remain as vapor forever. At some point, as it rises and the air around it cools, it must condense and must transform back into liquid water. Yet, here is where the mystery deepens. Water doesn't simply condense out of thin air on its own. It needs something to condense upon, something to serve as a seed or nucleus, around which the liquid water can gather. These seeds are everywhere. Dust particles rise from deserts and are carried by winds across entire continents and oceans. Salt crystals spray into the air from the ocean's surface when waves break. Pollen drifts on the breeze. Smoke particles from fires and volcanic ash fill the upper atmosphere. Tiny specks of pollution and soot rise from cities and factories. These particles, collectively called condensation nuclei, are the invisible scaffolding upon which clouds are built. When water vapor encounters one of these particles, something remarkable happens. The water vapor condenses directly onto the particle's surface, forming a microscopic layer of liquid water. More water molecules arrive and condense, layer after layer, until a tiny droplet has formed around the original particle. Billions of these processes happen simultaneously in the cubic kilometers of air, where a cloud forms. The result is a cloud, a visible clustering of countless water droplets, each one nucleated around a microscopic particle of dust, salt, or pollution. Different types of particles create different effects. Dust from the Sahara, when carried across the Atlantic to the Caribbean, creates particularly beautiful sunsets and affects cloud formation in those regions. Sea salt from ocean spray makes efficient condensation nuclei because salt attracts water molecules. Particles from volcanic eruptions can affect cloud formation patterns for years after the eruption, sometimes cooling the entire planet by a fraction of a degree as the particles interfere with sunlight. Think of it this way. If a cloud is a city, then the dust and salt particles are the foundations and frameworks around which the city is built. Without these foundations, the water vapor would have nowhere to condense, and clouds simply would not form. The tiny invisible particles that seem insignificant specks of dust, so small you cannot see them, are actually the essential structure upon which one of nature's most beautiful phenomena depends. This is one of the hidden partnerships in nature. Particles of matter that we might consider waste or pollution serve as the necessary scaffolding for clouds. Desert dust and sea salt, materials that travel thousands of miles through the atmosphere, end up playing crucial roles in the formation of clouds that provide water to ecosystems thousands of miles away. The Earth is far more connected than it appears. The air must cool for clouds to form, and it cools as it rises. If you hold a wet cloth in your hand, it feels cool as the water evaporates. This is because evaporation is an endothermic process. It requires energy, and that energy comes from the heat in your hand. The cloth cools as the water leaves it. The reverse process, condensation, is exothermic. It releases energy. When water vapor condenses into liquid water, it releases heat. But the key to forming clouds in the first place is that the air must cool enough for condensation to even become possible. Air cools in several ways in the atmosphere. The most important way is through expansion. When air rises, the atmospheric pressure around it decreases. Because pressure has decreased, the air expands. And when air expands, it cools. This is one of the fundamental principles of thermodynamics. It explains why it's colder at the top of a mountain than at its base, why it gets colder as you fly higher in an airplane, why air expelled from a can of compressed air feels cold. As warm air rises from the Earth's surface, heated by the sun, it expands and cools at what's called the adiabatic lapse rate, which is about 6.5 degrees Celsius per kilometer of altitude gain. As the air continues rising and cooling, it eventually reaches the dew point, the temperature at which air becomes saturated with water, vapor, and can hold no more moisture. At this critical point, condensation begins. Water vapor, which has been invisible in the air, suddenly transforms into visible liquid droplets. The altitude at which this happens is called the condensation level, and it's at this level that the base of the cloud forms. This is why clouds have such distinct horizontal bases. The condensation level is like a floor, a boundary below which the air is still too warm to allow condensation, and above which the cooling air allows it. Different conditions lead to different cloud bases. On a hot, humid day, the air becomes saturated quickly, and condensation begins at a lower altitude, resulting in low clouds. On a cool, dry day, the air may need to rise much higher before it becomes saturated, resulting in high clouds. This is why the sky's appearance, the altitude and density of clouds, changes with season and weather patterns. As the clouds continue to develop and water condenses, something else happens. The condensation itself releases heat, latent heat, which warms the surrounding air. This warming air becomes buoyant and rises further, drawing in more air from below, which rises and cools and condenses in turn. The process becomes self-reinforcing, leading to the development of taller, more substantial clouds. This is the fundamental engine behind cloud formation. Rising air, expansion, cooling, condensation, latent heat release, more rising. It's a cycle that repeats thousands of times every day across the planet, creating the endless variety of clouds we see in the sky. Cumulus clouds are the puffy, fair-weather clouds that dot summer skies. On a beautiful summer day, when the sun is warm but not oppressively hot, when there's a gentle breeze and the world feels perfect for lying outside, the sky often fills with cumulus clouds. These are the classic clouds of childhood imagination, the ones you see and immediately think of as cottages and castles and faces. Cumulus. Clouds form when warm air at the surface rises in discrete parcels or columns. A patch of dark pavement might heat up more than the surrounding grass, creating a rising column of warm air. A sunny side of a hill might produce more heating than the shady side, leading to air rising preferentially along that slope. These rising columns of air form at distinct locations, creating separate clouds that don't merge together. The result is a sky dotted with individual clouds, each one with a distinct identity and shape. The shape of a cumulus cloud is characteristic: a flat, horizontal base, and a billowing, rounded top. The flat base marks the condensation level below this level. The air is too warm for droplets to persist. The rounded, turbulent top marks the zone where new air is being incorporated into the cloud, where the air continues to rise and cool and condense. To look at a cumulus cloud is to watch the process of convection made visible. The air movement inside the cloud is continuous. Warm air rises up the middle of the cloud, while cooler air sinks around the edges. Moisture evaporates from the edges where the cloud interfaces with the drier surrounding air, while condensation continues in the rising core. The cloud is not a static object, but a dynamic process, a manifestation of energy flow and thermodynamic gradients. Cumulus clouds are the friendliest of clouds. They suggest good weather. They invite daydreaming. They are small enough to feel intimate and detailed, yet numerous enough to fill the sky with variety. They transform the sky into a canvas of possibilities. In the time it takes to watch them, they shift and change. A castle becomes a ship, becomes a face. The clouds are collaborators in human imagination, providing the raw material upon which our minds project meaning. When cumulus clouds remain relatively small and well separated, they indicate fair weather. The atmosphere is stable. The rising air is limited in extent. The clouds don't develop into anything more threatening. These are the clouds of perfect days, the ones that suggest nothing but sunshine for hours to come. But cumulus clouds can also be the harbingers of change. If the atmosphere is particularly unstable, if the surface is exceptionally hot, if the moisture content is high, then cumulus clouds can continue growing upward. They can stack atop one another, their billowing tops reaching higher and higher. They can transform from fair weather clouds into something more dramatic and potentially more dangerous. Stratus clouds form a complete layer across the sky, like a ceiling of gray. If cumulus clouds are the clouds of clarity and possibility, stratus clouds are the clouds of enclosure and mystery. A stratus cloud formation is a complete, continuous layer that stretches from horizon to horizon, covering the entire sky. There are no gaps, no blue sky visible, just an uniform gray overhead. Stratus clouds form when a layer of air is lifted gradually over a large area, rather than rising in discrete columns. A warm air mass moving over cool water will gradually cool and reach its dew point, forming a stratus layer. Warm, moist air forced to rise by a mountain range will form a stratus layer on the windward side. A layer of air that cools through the night may become saturated and form stratus by morning. The result is always the same: a complete, extensive cloud layer with a relatively uniform appearance. The base of a stratus cloud is often low, sometimes just a few hundred meters above the ground. In fact, when a stratus cloud forms very close to the surface, it's called fog. And fog is simply a cloud at ground level, made of the same minuscule water droplets as any other cloud, but close enough that we pass through it rather than admiring it from below. Stratus clouds create a particular quality of light. The sun is obscured but not entirely absent. The light diffuses through the cloud layer, creating an even, shadowless illumination. There is no sense of direction to the light, no shadows to indicate the sun's position. The world feels smaller, more intimate, more enclosed. The horizon shrinks to just a few kilometers away. The vast sky becomes a ceiling, a lid, a boundary. There is something both comforting and melancholic about stratus clouds. The world feels protected, sheltered from the vastness beyond, but it also feels confined, limited, cut off. For people sensitive to seasonal changes, Stratus clouds covering the sky for days can contribute to a sense of melancholy or depression. And yet, for others, they create a cozy, intimate feeling, as though the world has been drawn closer, made smaller, and more manageable. Stratus clouds are the least dramatic of cloud types. They produce light, rain, or drizzle rather than thunderstorms. They move slowly and change gradually. They lack the visual drama of cumulus clouds or the threatening appearance of cumulonimbus clouds. And yet, they cover vast areas of the planet much of the time. Over the oceans, particularly in certain latitudes, stratus clouds are a semi-permanent fixture, part of the climate system itself, rather than a temporary weather phenomenon. The presence of extensive stratus cloud layers affects the Earth's climate significantly. These clouds reflect sunlight back to space, cooling the planet. But they also trap heat radiating from the surface, warming the planet. The net effect depends on subtle details of the cloud's altitude, its thickness, and the properties of the air below it. Climate scientists study stratus clouds intensively because changes in their extent and properties could have profound implications for Earth's climate. Altocumulus clouds arrange themselves in patterns that seem almost geometric. Higher in the sky, at altitudes of around 2 to 6 kilometers, lives another cloud family, the altocumulus clouds. These are smaller than cumulus clouds, more delicate, often arranged in patterns that seem almost too regular to be natural. Altocumulus clouds often form in parallel rows or in honeycomb-like patterns. When you look up and see the sky covered in thousands of small, puffy clouds, all similarly sized, all arranged in lines or grids, you're seeing altocumulus clouds. These patterns form through a process called convective organization. Warm air rises in some locations and cooler air sinks in others, creating a regular pattern of updrafts and downdrafts. Clouds form in the updraft regions, leaving gaps in the downdraft regions. The result is a remarkably orderly-looking pattern that emerges spontaneously from the chaotic interaction of air parcels. These patterns are often called cloud streets or cloud streets, and they're one of the most visually striking manifestations of atmospheric dynamics. From the ground, looking up, you see a pattern that seems almost constructed, almost artificial. From an airplane or satellite, you see it even more clearly. Long, linear patterns of clouds running parallel to one another, as though someone has organized them carefully. And yet, no one organized them. They emerged from the simple physics of differential heating and cooling, of air rising and sinking, of water vapor condensing around dust particles. The geometric beauty of these patterns is not designed, but discovered. It's the inevitable outcome of natural laws operating on a large scale. This is one of the profound insights that atmospheric science offers. Order emerges spontaneously from chaos. Patterns arise naturally from the interaction of simple physical rules. Altocumulus clouds appear during mid-morning hours, as the surface heating increases and convection strengthens. They disappear in the evening as heating decreases. They're temporary, ephemeral, lasting only hours before reorganizing or dissipating. But during their existence, they create visual poetry, patterns of such regularity and beauty that they seem almost intentional. Different altitudes and latitudes favor different pattern types. In some regions and seasons, altocumulus clouds arrange themselves in a honeycomb pattern, each cloud touching its neighbors, creating a grid of hexagons. In other regions, they form parallel lines. Still in others, they take on spiral or curved patterns. Each variation reveals something about the atmospheric conditions at that moment, in that place. Looking at altocumulus clouds and observing their patterns is a way of reading the atmosphere, of understanding the invisible forces at work above your head. The clouds are a text written in the sky, and those who learn to read them can predict changes in weather, can understand the hidden dynamics of the atmosphere, can feel connected to the larger systems within which they live. Cirrus clouds form at high altitudes, where its so-called water freezes directly into ice crystals, much higher in the sky, at altitudes of 5 to 13 kilometers, where the air is so cold that water freezes instantly. Another cloud type emerges, the cirrus clouds. These are delicate, wispy, often appearing as thin brushstrokes across the sky. Cirrus clouds form not from water droplets, but from ice crystals. At these high altitudes, the temperature is so far below freezing that water vapor can transform directly into ice without passing through a liquid phase. This process is called deposition. It's the same process that creates frost on windows in winter. Water vapor in the air condenses directly into ice crystals on the cold glass. In the upper atmosphere, these ice crystals form around the same condensation nuclei as liquid droplets, particles of dust and salt and pollution. But because of the extreme cold, the resulting clouds are made of ice rather than water, and ice crystals have very different properties than water droplets. They refract light differently, creating optical phenomena like halos and light pillars. Cirrus clouds are beautiful precisely because they're made of ice crystals. The crystals catch light from different angles, creating patterns of reflected and refracted light that are far more complex than what occurs in water droplet clouds. A single cirrus cloud often exhibits bands of light and shadow, subtle color effects, and extraordinary delicacy. The shapes of cirrus clouds are remarkably varied. Some form as thin, uniform layers. Others create the classic wispy brushstroke appearance, as though the sky has been painted with a very fine brush. Still others take on the appearance of feathers or curled locks of hair. These varied appearances reflect different processes of ice crystal formation and orientation within the cloud. Cirrus clouds also move differently than lower clouds. At these high altitudes, wind speeds are often much stronger than at lower levels. A jet stream, a narrow band of very strong wind flowing at high altitudes, can push cirrus clouds at speeds of over 100 kilometers per hour. To watch a cirrus cloud move is to watch the upper atmosphere in motion, to see evidence of winds far stronger than any we feel on the surface. Interestingly, cirrus clouds can affect Earth's climate in complex ways. They're thin enough that sunlight passes through them easily, so they don't reflect much solar radiation. But they're quite good at absorbing and re-radiating infrared radiation, the heat radiating from Earth's surface. This means that cirrus clouds tend to trap heat, warming the planet. This is one of the ways that clouds affect climate. Different types of clouds have different effects on the balance of energy entering and leaving the Earth system. Cumulonimbus clouds are towering giants that reach the edge of space. If cumulus clouds are the gentle clouds of summer, and stratus clouds are the quiet clouds of autumn mornings, then cumulonimbus clouds are the titans of the sky, the clouds of drama and power and weather-changing significance. Cumulonimbus clouds form when convection is extreme. The surface is very hot, the air is very moist, and there's strong vertical wind shear winds changing direction and speed with altitude. Under these conditions, rising air parcels don't stop at moderate heights. They continue rising, higher and higher, their ascending motion accelerated by the continuous release of latent heat as water condenses. The result is a cloud of extraordinary vertical development. While a typical cumulus cloud might reach 1 or 2 kilometers in vertical extent, a cumulonimbus cloud can reach 10, 15, or even 20 kilometers high. At these extreme altitudes, the cloud top encounters the stratosphere, a stable layer of air that actively resists further upward motion. The cloud's top flattens out, spreading horizontally, creating the classic anvil shape that cumulonimbus clouds are famous for. Inside a cumulonimbus cloud, the dynamics are extraordinarily violent. Updrafts of air rise at speeds of over 100 kilometers per hour, sometimes much faster. These updrafts carry huge quantities of water droplets upward to altitudes where they freeze into ice crystals. Meanwhile, downdrafts of cold, heavy air sink back down at equally impressive speeds. The result is a chaotic, violent, internal structure. This violence manifests in multiple ways. Cumulonimbus clouds produce heavy rain, not the gentle drizzle of stratus clouds, but intense downpours. They produce lightning, one of nature's most dramatic electrical phenomena. They produce hail, as ice crystals formed high in the cloud get caught in downdrafts, fall partway, then get caught in updrafts again, rising and freezing more layers of ice around themselves, finally falling to the ground as balls of ice. They produce tornadoes, rotating vortices of air that descend from the cloud base and touch the ground. To stand beneath a cumulonimbus cloud is to feel small in the face of nature's power. The cloud fills the entire sky, towering miles overhead, its base dark and ominous, its interior churning with invisible violence. The wind strengthens, the air pressure drops noticeably, the temperature falls as cold air from high altitude descends. Birds stop singing and seek shelter. The entire world seems to pause, waiting for what comes next. And yet, cumulonimbus clouds are also essential. They transport vast quantities of water, creating the heavy rains that replenish rivers and aquifers. They help regulate Earth's energy balance, transporting heat from the surface to the upper atmosphere. They create the electrical phenomena of lightning, which fixes nitrogen in the atmosphere, making it available for plant use. The same cloud that seems threatening is also performing essential work for the planetary system. Lenticular clouds hover above mountains, like stationary UFOs. In certain locations, particularly downwind from mountain ranges, there forms a most unusual cloud, the lenticular cloud. These clouds seem almost stationary, hanging in place above a mountain peak as though fixed to the landscape itself. Their smooth, lens-like shape and their apparent stillness have led to countless UFO sightings and alien encounter reports. Lenticular clouds form when moist air is forced to rise by a mountain. As the air rises on the windward side of the mountain, it expands and cools, eventually reaching its dew point and forming a cloud. As the air continues over the peak and descends on the leeward side, it warms again, and the cloud evaporates. If the wind speed and direction remain constant, then the air on the windward side continuously forms a cloud, while the cloud on the leeward side continuously evaporates. The result is a cloud that appears stationary, always occupying the same position relative to the mountain, even though the air within it is constantly flowing through. The shape of the lenticular cloud is determined by the shape of the mountain and the wind flow over it. Typically, these clouds have a smooth, lens-like or almond-like appearance. Some lenticular clouds stack atop one another, creating a series of lens-shaped formations, one above the other. Others take on more complex shapes, creating formations that look almost sculptural, almost artificial. The smoothness of lenticular clouds is remarkable. Most clouds have billowing, turbulent tops, their boundaries unclear and shifting. But lenticular clouds often have sharp, well-defined edges, smooth surfaces. This smoothness reveals the nature of the airflow beneath the cloud. The air is moving smoothly and uniformly, following the contours of the mountain in a laminar flow. There are no strong updrafts or downdrafts, no turbulent mixing. The flow is orderly, predictable, serene. For pilots, lenticular clouds have both beauty and danger. The smooth appearance is deceptive. Beneath the smooth exterior of a lenticular cloud is often extremely rough air, powerful updrafts and downdrafts, strong wind shear. Aircraft that enter a lenticular cloud unprepared can be tossed around violently, leading pilots to call these clouds rotors. The beautiful exterior hides violent interior dynamics. Lenticular clouds are found wherever mountains reach high enough to force air to rise significantly. In the Rocky Mountains, the Andes, the Alps, and the Himalayas, lenticular clouds are common sights on days when the upper-level wind speed is strong and consistent. These clouds are stationary enough that the same cloud can be seen in the same position for hours as one generation of cloud replaces the previous one at the same location. To watch a lenticular cloud is to watch a fundamental principle of atmospheric dynamics made visible. The principle is simple. When moist air is forced to move up and down, it alternately cools and warms, condenses and evaporates. If the forcing is continuous and regular, the cloud that forms will be continuous and regular as well, appearing frozen in place even though the air within it is in constant motion. Mammatus clouds create pouches that drape from the cloud base like breasts. In the aftermath of a thunderstorm, when the sky is clearing but still turbulent, a most unusual cloud formation sometimes appears: mammatus clouds. These are clouds with pronounced pouches or pendants hanging down from the cloud base, as though the cloud is sagging under some invisible weight. Mammatus clouds form when there is a sharp density discontinuity between layers of air, one layer much colder and denser than the layer below it. Cold air sinking in some locations and warmer air rising in others create a pattern of small-scale convection. But because the lower warm air is preventing the downward moving air from reaching the surface, the convection cannot fully resolve. Instead, the air movement is confined to the layer between the warm air below and the cold air above. This creates the characteristic pouches, which are regions of sinking air, and the protrusions between them, which are regions of rising air. The visual effect is striking. A cloud ceiling appears to have bubble-like protrusions hanging down from its base. The pouches can be a few hundred meters across and can hang down for several hundred meters, creating a three-dimensional appearance that contrasts sharply with the usual two-dimensional appearance of clouds viewed from below. Mammatus clouds often appear in the aftermath of severe weather, when the atmosphere is still disorganized and turbulent. They seem to be a manifestation of the atmosphere attempting to reorganize itself, of instability expressing itself in three-dimensional form before dissipating into stability. Because of their unusual appearance, mammatus clouds have acquired folklore and significance in many cultures. Some indigenous peoples have seen them as portents of weather change. Some modern observers have speculated about their significance for tornado formation or severe weather. In reality, while mammatus clouds often appear with severe weather, they're not a reliable predictor of future weather. They're interesting, primarily because they reveal the three-dimensional dynamics of the atmosphere, showing us something that's usually invisible. To look at mammatus clouds is to look at the atmosphere's internal struggles made visible. The pouches are like a window into turbulence and instability. They remind us that the sky above is not a static, peaceful place, but a dynamic, energetic realm, where millions of tons of air are continuously in motion, rising and sinking, warming and cooling, organizing and reorganizing themselves according to principles of physics that seem almost alive. Noctilucent clouds glow silver blue in the twilight at the edge of space, higher than any other cloud type, at altitudes of 75 to 85 kilometers above the stratosphere. Exists a rare and beautiful cloud phenomenon, noctilucent clouds. These clouds glow an ethereal silver blue in the twilight hours, visible when the sun has set for observers on the ground, but is still illuminating the clouds at great altitude. Noctilucent clouds form in the mesosphere, a layer of atmosphere so cold that water freezes directly into ice crystals, even though the concentration of water vapor is infinitesimal. These clouds form around microscopic particles, likely dust from meteors that burn up in the upper atmosphere, or possibly particles from volcanic eruptions in the stratosphere. The appearance of noctilucent clouds is otherworldly. They often have a wavy or herringbone pattern, or they may resemble something like mother-of-pearl clouds with iridescent colors. They glow with a blue or silver luminescence, seemingly self-illuminated, though they're actually reflecting sunlight from well below the horizon. They cover areas of sky measured in thousands of square kilometers and seem to move with fluid grace through the thin air at the edge of space. For most of human history, noctilucent clouds were extremely rare. They were documented occasionally, but seen by few. On the last 50 years, they have become more frequent, appearing in the twilight sky multiple times in a single summer month in mid-latitudes. Scientists believe this increase is related to rising methane levels. In the atmosphere, methane allows more water to reach the mesosphere, where it condenses into clouds. To see noctilucent clouds is to see the highest clouds in Earth's atmosphere, to witness a phenomenon that occurs at the boundary between atmosphere and space, where the air is so thin that it hardly seems like air at all. The clouds seem to belong as much to space as to Earth, to be almost not of this world. The word cloud comes from ancient Germanic roots, meaning clod of earth or mass. Language itself contains clues about how humans have understood clouds. The word cloud comes from ancient Germanic and Old English roots that originally meant clod of earth or lump or mass. Early English speakers saw clouds in the sky and thought of them as lumpy masses, similar to lumps of earth or clods of soil. This etymology reveals something about human perception. We don't perceive things as they truly are, but through metaphor and comparison to what we already know. Clouds, floating in the sky, were conceptualized as Earth-like lumps because they had a lumpy, massive appearance. The metaphor is apt. Clouds do look lumpy. They do look substantial. They do seem to have mass and weight, even though they're mostly empty air. Different languages have taken different paths with their cloud terminology. The French word nuage comes from the Latin nubile, related to nubis, meaning cloud, but also to concepts of darkness and obscurity. German Wolke comes from Indo-European roots, related to rolling or turning, capturing the sense of clouds drifting and transforming. Japanese has preserved ancient distinctions between different types of clouds that relate to their mystical and poetic significance. The scientific classification of clouds, the taxonomy, we use today was developed primarily by Luke Howard in the early 1800s. Howard proposed the terms cumulus, stratus, and cirrus, which have become the foundation of cloud classification. These Latin-based terms allowed for a more objective, systematic approach to cloud classification than had existed before. Howard's system was a turning point in treating clouds as scientific objects rather than merely poetic subjects. Howard's innovation was significant because it allowed people with different native languages to communicate about clouds using the same terminology. It created a common language for cloud observation, standardizing what people saw and how they described it. Before Howard, cloud observation was haphazard, impressionistic, subjective. After Howard, it became possible to create a global system of cloud observation with different observers in different countries using the same classification system. Today, cloud classification has become far more detailed and sophisticated. We distinguish dozens of cloud types and subtypes based on altitude, formation mechanism, and appearance. But the foundation still rests on Howard's original insight, that clouds could be classified systematically, that the diversity of cloud forms could be organized into a manageable taxonomy, that language and systematic observation could bring order to what had seemed chaotic and random. Clouds have been painted by artists for thousands of years, For as long as humans have produced visual art, they have been drawn to painting clouds. In Chinese landscape painting, which dates back over 1,000 years, clouds are not mere background but central subjects. The great painters of the Song dynasty and later periods devoted extraordinary attention to rendering clouds accurately and beautifully. Clouds were understood as manifestations of the Tao, the fundamental principle underlying all nature. To paint clouds accurately was to approach an understanding of nature's fundamental essence. European landscape painting largely ignored clouds until the Romantic era, when there was a renewed interest in nature in all its forms. John Constable, an English painter, became famous for his studies of clouds. He would go out in all kinds of weather, with sketchbook in hand, and fill page after page with quick studies of different cloud formations, different times of day, different qualities of light. Constable understood that to paint convincing landscapes, one must study clouds with the same intensity that one studies the land. He wrote that the sky was the keynote of a landscape painting. Without an accurate, dynamic, believable sky, even the most carefully rendered trees and fields would feel lifeless and unconvincing. This insight that the sky is fundamental to a landscape's emotional and aesthetic impact transformed how artists approached their work. Clouds inspire meteorologists and weather forecasters to predict the future. Long before we had satellites and radar and supercomputers, humans predicted weather by observing clouds. A person experienced in reading clouds could look at the sky and make reasonable predictions about what weather was coming. These predictions were often remarkably accurate, based on decades or centuries of accumulated observation. Different cloud formations carry different meteorological meanings. Cumulus clouds with flat bases in early morning suggest fair weather through midday, but possible thunderstorms in the afternoon as heating increases. Altocumulus clouds in parallel rows suggest wind shear at altitude and possible strong winds at the surface later in the day. Cirrus clouds spreading across the sky often indicate that a warm front is approaching and rain will likely arrive within 24 hours. Farmers learned to read these signs as a necessary part of their work. Harvest timing, field burning, irrigation decisions all required accurate weather prediction. A farmer who could read clouds well might make decisions that meant the difference between a successful harvest and crop loss. This knowledge was passed down through generations, accumulated and refined, tested against reality thousands of times. Even today, with all our modern technology, meteorologists and experienced weather observers find value in cloud observation. Cloud patterns visible in the sky provide information about atmospheric conditions and processes that may not yet be apparent in instrument readings. A skilled observer can often detect changes in the atmosphere hours before they show up in radar or satellite data. This connection between clouds and weather prediction has deep historical roots. In many cultures, certain cloud types have folklore associated with them. A red sky at sunset and a red sky at sunrise have different meanings. Red sky at night, sailors delight. Red sky in morning, sailor take warning. This rhyming couplet encodes a genuine meteorological observation. A red sky at sunset indicates that high pressure is moving in from the west, where the sun is, bringing fair weather. A red sky at morning indicates moisture in the air and clouds, often associated with departing fair weather and incoming storms. These folk sayings aren't perfect. Nature is more complex and variable than any rhyme can capture. But they represent the accumulated wisdom of countless observations, a kind of distributed, collective cloud knowledge that emerged from necessity. Weather affected survival, so people paid attention to clouds. The water cycle depends entirely on clouds as the mechanism for transporting water. The water cycle, the endless circulation of water between ocean, atmosphere, and land, is one of Earth's fundamental processes, and clouds are central to it. Water evaporates from oceans, lakes, and rivers. It rises as invisible vapor. But somewhere, somehow, this water must condense and return to the surface as precipitation. Clouds are the mechanism through which this occurs. Without clouds, the water cycle would grind to a halt. Water would evaporate from the oceans, but it would have nowhere to condense. It would accumulate in the atmosphere as vapor until the atmosphere was completely saturated. Eventually, a kind of equilibrium would be reached, where the rate of evaporation equaled the rate of precipitation from a saturated atmosphere. But without clouds, there would be no rain over land, no fresh water to sustain life away from the oceans. The fact that clouds form and that precipitation falls is what makes terrestrial life possible. Rivers exist because clouds deliver water inland. Forests grow where rain falls regularly. Grasslands, deserts, savannas, their character is defined by the patterns of precipitation, which is controlled by clouds. Essentially, every ecosystem on land depends on the clouds overhead and what they deliver. Different regions receive different amounts of precipitation based on cloud patterns. Some regions are persistently cloudy and rainy, receiving hundreds of centimeters of precipitation annually. Other regions are persistently dry, with clouds forming rarely and precipitating even more rarely. The Atacama Desert in South America is one of the driest places on Earth, with some regions receiving no measurable rain for decades. This extreme aridity results from atmospheric circulation patterns that suppress cloud formation in those latitudes. Over the oceans, different patterns emerge. Some ocean regions are persistently clear with few clouds, while others are persistently cloudy. Tradewind regions often have steady stratus cloud decks over the ocean. Tropical regions often have tall, towering cumulonimbus clouds. The patterns of cloud coverage over the oceans have profound effects on heat transport, on the formation of hurricanes, on fish populations, on ocean currents. The relationship between clouds and the water cycle is intimate and complex. More water precipitates in regions where clouds are persistent and well developed. Less water precipitates in regions where clouds are scarce. The patterns of where clouds form determine where water is available, which determines where life can flourish. In a very real sense, clouds write the geography of habitability on Earth's surface. Clouds transport moisture across continents, delivering rain to inland regions far from the ocean. One of the most underappreciated facts about clouds is that they transport water across vast distances. Water evaporates from the Atlantic Ocean and is carried inland by winds, eventually precipitating as rain over the Amazon rainforest. Water evaporates from the Pacific Ocean and is carried inland by winds, precipitating as rain over the Rocky Mountains. Water evaporates from the Indian Ocean and is carried by monsoon winds, delivering essential rains to agriculture-dependent India and Southeast Asia. This transport of moisture is critical for inland ecosystems and human agriculture. The Amazon rainforest itself contributes to this process. It evaporates enormous quantities of water, which then condenses into clouds, which fall as rain. If the forest were removed and replaced with pasture or crops, the evaporation would decrease, the clouds would decrease, and the rainfall would decrease. The forest would gradually dry out, eventually reaching a tipping point where it could no longer sustain itself. The forest and its clouds are in a feedback loop, each dependent on the other. On a global scale, clouds and the moisture they transport are essential for climate regulation. Moisture transport from oceans to continents moderates temperature differences. Without this transport, continents would be even hotter in summer and colder in winter. The global distribution of heat, which is one of the fundamental drivers of weather and climate, depends critically on clouds and the water they transport. Different seasons bring different patterns of cloud formation and moisture transport. Monsoon regions experience dramatic seasonal shifts, with the dry season characterized by few clouds and intense heat, and the wet season characterized by persistent clouds and abundant rain. These seasonal patterns have shaped human civilization in these regions, determining when crops are planted and harvested, when travel is possible, when festivals occur. The moisture that clouds carry can be visualized by climate scientists using atmospheric models and satellite observations. They can trace rivers of moisture in the atmosphere, corridors where enormous quantities of water vapor flow from ocean toward land. These atmospheric rivers can be hundreds of kilometers wide and thousands of kilometers long. When they arrive over land, they often produce intense rainfall and flooding. When they are diverted or weakened, they can result in drought. Understanding these patterns of moisture transport has become increasingly important as climate change alters rainfall patterns. Some regions are becoming wetter as warming atmosphere can hold more moisture, but the distribution of this moisture is changing. Some regions are becoming drier as atmospheric circulation patterns shift. The clouds, the manifestations of these moisture patterns, show us directly where the water is going. Clouds reflect sunlight back to space, providing cooling that moderates Earth's temperature. One of the most critical roles clouds play in Earth's climate system is that they reflect sunlight back to space. This albedo effect, the reflection of sunlight, is one of the primary ways that clouds cool the planet. Estimates suggest that clouds reflect roughly 30% of the incoming solar radiation. Without clouds, Earth would be significantly warmer. The cooling effect of clouds is particularly strong during the day, when the sun is high in the sky and shining intensely. A thick cloud layer can block nearly all the sunlight, reducing the solar radiation reaching the surface to just a fraction of what it would be on a clear day. Anyone who has experienced a warm, sunny day, suddenly becoming cool as a large cloud passes overhead, has felt this effect directly. Different types of clouds have different albedos, different abilities to reflect sunlight. Thick cumulus clouds reflect more light than thin cirrus clouds. Low, dense stratus clouds reflect more than high, wispy clouds. Bright white clouds reflect more than clouds tinged with the darkness of their own shadows and interior. In general, clouds closer to the surface reflect more sunlight than high-altitude clouds, because there's more atmosphere below them to absorb some of the light before it reaches the surface. This is where things become complex. While all clouds reflect some sunlight and provide cooling, the nighttime effect of clouds is different. At night, clouds trap heat, radiating from Earth's surface, and re-radiate it back downward, warming the planet. This trapping of outgoing radiation is called the greenhouse effect, and clouds contribute to it. The net effect of clouds on climate depends on the balance between their daytime cooling through albedo and their nighttime warming through greenhouse effect. For some cloud types and altitudes, cooling dominates. For others, warming dominates. High, thin cirrus clouds tend to trap more heat than they reflect, because they're thin and transparent to sunlight, but still significant in infrared opacity. Low, thick stratus clouds tend to reflect more heat than they trap. The average effect of clouds globally appears to be a net cooling of about 5 to 10 watts per square meter. This cooling is significant enough that if all clouds were to suddenly disappear, Earth would warm substantially, potentially by several degrees Celsius. Climate scientists studying clouds are concerned about how changes in cloud coverage and cloud types might affect future climate. If greenhouse warming causes clouds to become higher and thinner because the atmosphere is warmer, the greenhouse warming effect of clouds might increase, while the cooling effect decreases. This would represent a positive feedback warming, leading to cloud changes that cause more warming. Conversely, if clouds become more numerous or more reflective, this could provide negative feedback, warming, leading to cloud changes that cause cooling. These cloud feedback processes are among the largest sources of uncertainty in climate change projections. Small changes in how clouds behave could mean the difference between moderate warming and severe warming. This is why climate scientists devote so much effort to studying clouds, to making satellite measurements of cloud properties, to running sophisticated models of cloud formation and behavior. Clouds help distribute heat from the equator toward the poles. In addition to reflecting sunlight, clouds play another critical role in Earth's energy balance. They help transport heat. Warm, moist air rises at the equator, where solar heating is most intense. This air carries latent heat, the energy stored in water vapor. As the air rises and cools, water condenses into clouds. When water condenses, it releases this latent heat, warming the surrounding air. This heat is then transported poleward by atmospheric circulation patterns. The heat that was picked up as water vapor at the equator is released in clouds at higher latitudes. This heat transport is one of the primary ways that the poles receive energy and remain warmer than they would be from direct solar heating alone. Without this heat transport via clouds and water vapor, the poles would be much colder and the equator would be even hotter. This heat transport is essential for planetary habitability. It moderates the temperature gradient between equator and poles. If all the heat stayed concentrated at the equator, the equatorial regions would be incomprehensibly hot, and the polar regions would be incomprehensibly cold. Life could not exist in such extreme conditions over most of the planet. Hurricanes are an extreme manifestation of this heat transport mechanism. These massive storm systems form over warm ocean water, drawing enormous quantities of warm, moist air upward. As the water vapor condenses in the rising air, it releases vast amounts of latent heat, which drives the storm. The hurricane is essentially a giant heat engine, powered by the conversion of latent heat to kinetic energy in the wind. The hurricane transports this heat from the tropical oceans toward higher latitudes. The heat transport function of clouds explains why cloud systems are so often associated with large-scale weather patterns. A cold front represents an intrusion of cold, dry air from the poles. Where the cold air encounters warm, moist air, clouds form and rain falls. The boundary between air masses is where the most dramatic cloud formation and precipitation occurs, because it's where the temperature and moisture contrasts are greatest. Clouds cause lightning, one of nature's most violent electrical phenomena. Inside a cumulonimbus cloud, conditions are extreme. There are powerful updrafts and downdrafts, ice crystals being tossed around violently, air being compressed and expanded, electric charges accumulating. In these extreme conditions, lightning can be generated. Lightning forms through a process that scientists still don't entirely understand. What we know is that electrical charge separation occurs within the cloud, with positive charges accumulating in some regions and negative charges in others. Eventually, the electrical potential difference becomes so great that the air's insulating properties break down. Electricity flows suddenly, seeking the path of least resistance. This sudden flow of electricity is lightning. The temperature of a lightning channel is extraordinary, around 30,000 Kelvin, hotter than the surface of the sun. This extreme heat causes the air in the lightning channel to expand, explosively, creating a shock wave. This shock wave is what we hear as thunder, the sound of air being torn apart by the sudden expansion. Lightning travels at incredible speeds, roughly 1/3 the speed of light. From cloud to ground, a lightning bolt can travel kilometers in just microseconds. The light reaches our eyes essentially instantaneously, which is why we see lightning before we hear the thunder. The sound of thunder takes longer to reach us because sound travels much more slowly than light, roughly 340 meters per second. By counting the seconds between flash and boom and dividing by 3, we can estimate the distance to a lightning strike. For humans, lightning represents both fascination and danger. Lightning strikes kill thousands of people annually worldwide and cause millions of dollars in damage. And yet, lightning has been culturally significant throughout history. Many cultures have seen lightning as an expression of divine power or anger. Deities controlling lightning: Zeus in Greek mythology, Thor in Norse mythology, Indra in Vedic mythology, occupy central places in religious belief. Indigenous cultures developed lightning-related rituals and protective practices based on long observation of lightning behavior. Modern science has revealed that lightning strikes are not random, but follow certain patterns. Lightning tends to strike the tallest objects in an area. It tends to strike near the borders of storm clouds, where the greatest charge separation occurs. It tends to be attracted to pointed objects and to objects that conduct electricity. This knowledge has led to the development of lightning rods, metal conductors that guide lightning safely into the ground rather than allowing it to strike a building or a person. Interestingly, lightning has beneficial effects despite its danger. Lightning generates extreme temperatures and pressures that can break nitrogen molecules and recombine them into forms that can be used by plants. This process, called nitrogen fixation, adds usable nitrogen to the soil. Lightning also generates ozone, which affects atmospheric chemistry. The electrical phenomena of clouds have environmental effects far beyond their immediate dramatic appearance. Rain falls from clouds in a process that requires the right conditions to occur. Not all clouds produce rain. Many clouds evaporate and drift away without ever precipitating a drop. For rain to form and fall, specific conditions must exist. A cloud droplet is very small, about 10 to 20 micrometers in diameter. A raindrop is much larger, about 1,000 to 2,000 micrometers in diameter. For a raindrop to form from a cloud, billions of cloud droplets must somehow combine. They cannot simply merge on their own. Cloud droplets are so small and so numerous that they would take an extraordinarily long time to randomly collide and merge into raindrops. Instead, raindrops form through a process called coalescence. In a vigorous cloud, particularly in a cumulonimbus cloud, air currents cause cloud droplets to collide. When they collide, they stick together, forming slightly larger droplets. These larger droplets collide with other droplets more frequently because their larger size catches them in more air currents. As they grow larger, they continue colliding with and capturing smaller droplets. Eventually, they grow large enough that they fall through the air faster than smaller droplets. So they begin to fall even as the updraft tries to hold them aloft. Once a droplet becomes heavy enough that its terminal velocity exceeds the speed of the updraft, it falls. It continues falling, capturing more droplets as it falls, growing larger as it descends. By the time it reaches the ground, it has grown to perhaps 100 times its original size. This is a raindrop. The formation of raindrops depends critically on turbulence within the cloud. A calm, smooth cloud will not produce rain, even if it has considerable liquid water content. The droplets simply don't collide frequently enough for coalescence to occur. But a turbulent, vigorous cloud produces collisions rapidly, and rain forms quickly. This is why certain types of clouds produce rain readily, while others rarely do. A cumulonimbus cloud, with its violent internal motions, will produce rain and hail extensively. A weak cumulus cloud, with gentle internal motions, might evaporate without ever producing rain. A stratus cloud layer, often quite uniform and smooth, frequently drifts across a region without producing rain, or producing only light drizzle. The rate at which rain falls depends on how much liquid water is present in the cloud and how efficiently that water is being converted to raindrops. A dense cumulonimbus cloud can produce rainfall rates exceeding 100 millimeters per hour, more than an inch of rain, in just 60 minutes. A light stratus layer might produce rain at a rate of 1 or 2 millimeters per hour, barely perceptible as anything more than a light mist. Hail forms in powerful updrafts where droplets are repeatedly frozen and melted. In the most powerful cumulonimbus clouds, vertical air motion can exceed 100 kilometers per hour. These extreme updrafts carry water droplets to enormous altitudes, where the air is so cold that water freezes instantly. When water droplets freeze, they form ice crystals. These ice crystals are carried to even higher altitudes by the updraft, where they encounter supercooled water droplets, liquid water, existing at temperatures below freezing, because the water is so pure and isolated that it hasn't crystallized. When ice crystals collide with supercooled droplets, the droplets instantly freeze onto the crystal surface, forming a layer of ice. The ice crystal, now heavier because of the layer of ice around it, falls back down through the cloud. As it falls, it enters warmer air, and its surface begins to melt slightly. As it melts, it also encounters more supercooled droplets, which freeze onto its surface, adding another layer of ice. The crystal continues to fall, melting slightly, then getting caught in an updraft again, rising back into the upper levels of the cloud where it freezes again. This process repeats multiple times. Each time the ice particle is carried up and down through the cloud, it gains another layer of ice. The result is a hailstone, a ball of ice built up from concentric layers, each layer representing one trip through the cloud. When you cut a hailstone in half, you can see these layers, much like the rings on a tree. The number of layers indicates how many times the hailstone cycled up and down through the cloud. The size of the hailstone indicates how long it stayed in the cloud and how many layers it accumulated. A hailstone the size of a pea represents relatively brief cycling. A hailstone the size of a golf ball represents many more cycles. Extreme hailstones, the size of softballs or larger, represent extraordinary numbers of cycles and reflect conditions of extreme instability in the cloud. Hail can cause significant damage. Large hail can break windows, dent vehicles, damage crops, and injure people. There are hail alley regions on Earth, particularly in parts of the Great Plains of North America where hail occurs frequently enough that it's a regular hazard. In these regions, farmers have adapted by planting crops that are more resistant to hail damage, by constructing hail-resistant structures, and in some cases, by attempting weather modification to reduce hail formation, though the effectiveness of these efforts remains debated. The formation of hail shows how extreme the conditions inside a cumulonimbus cloud are. The updrafts are powerful enough to suspend balls of ice weighing hundreds of grams. The temperature variations within the cloud are extreme. The dynamics are as violent as anything found in Earth's atmosphere outside of a tornado. Snow forms when ice crystals accumulate and become heavy enough to fall. Not all precipitation falls as rain or hail. In many parts of the world, and in seasonal patterns in other parts, precipitation falls as snow. Snow forms in a process similar to hail, but with different end results. Ice crystals form in clouds, where the temperature is below freezing. These crystals grow by a process called deposition, water vapor, converting directly to ice, and by collecting supercooled droplets. As the crystals grow and become heavy enough, they fall through the cloud. Unlike hail, which is formed by repeated cycling through extreme updrafts, snow crystals fall more gently through the cloud, accumulating layers of ice as they encounter supercooled droplets. and sometimes even encountering other ice crystals and sticking to them, forming aggregates. By the time a snow crystal reaches the ground, it may have collected many other crystals, forming a snowflake, an aggregation of ice crystals stuck together. A snowflake can contain hundreds or thousands of ice crystals, creating the often beautiful, complex structures we associate with snowflakes. The shape of ice crystals in clouds is determined by the temperature and humidity conditions in the cloud. At certain temperature ranges, ice crystals form as needles. At other temperatures, they form as plates. At other temperatures, they form as dendrites, the classic six-pointed snowflake shapes. Snow crystals are among the most beautifully complex structures in nature, each one unique in its detailed structure, while maintaining the basic six-fold symmetry that characterizes ice crystals. Snow is critical for Earth's albedo and climate. Snow-covered surfaces reflect much more sunlight than bare ground or ocean. A snow-covered landscape can have an albedo of 80 or 90%, while open water might have an albedo of 10%. This high albedo of snow has profound implications for climate. The presence or absence of snow cover can determine whether a region receives enough solar heating to remain warm or whether it remains cold and frozen. Fog is a cloud that forms at ground level and reduces visibility dramatically. If a cloud forms very close to the ground, its name changes. Instead of calling it a cloud, we call it fog. Fog is simply a stratus cloud at ground level, made of exactly the same tiny water droplets as any other cloud, but close enough that humans and animals can walk through it. Fog reduces visibility dramatically. In heavy fog, visibility might be reduced to just a few meters. Driving through fog requires extreme caution because the normal visual cues for depth and distance are obscured. Airports close when fog reduces visibility below certain thresholds because aircraft cannot land safely. Fog forms through several mechanisms. In some cases, cool, moist air moves over warmer water, warming the air's lower layers and causing it to rise, eventually cooling and condensing into fog as it mixes with cooler air above. This is why coastal areas and regions downwind of warm water bodies often have fog. In other cases, air cools through radiation loss at night, reaching its dew point and forming fog at ground level. In some regions, fog is a regular and persistent phenomenon. San Francisco Bay is famous for its summer fog, which rolls in nearly every evening and fills the valleys. This fog is produced by the interaction of cool ocean water and warm inland air, with the fog flowing like a river through the Golden Gate and into the bay. The redwood forests of Northern California depend on this summer fog for moisture. They intercept fog droplets on their needles, and this moisture drips to the ground, providing essential water during the dry season. Fog has played important roles in human history. Naval battles and military maneuvers have been decided by the presence or absence of fog, which provided concealment and reduced visibility. Pollution-enhanced fog events have caused public health crises, most famously the Great Smog of London in 1952, which killed thousands. The fog trapped pollutants near the ground, creating a toxic haze that caused respiratory deaths. But fog also has aesthetic and cultural significance. Fog is associated with mystery, with the hidden and the unknown. In literature and film, fog often signals danger or the presence of something unknown. Japanese haiku poets have written extensively about fog, capturing its ethereal, transient quality. The image of fog-shrouded landscapes evokes a sense of beauty, mixed with slight unease, of nature in one of its more mysterious moods. Clouds contain minerals and dust that travel vast distances and affect distant ecosystems. When dust from the Sahara Desert is swept into the atmosphere by wind, it travels eastward across the Atlantic Ocean. Some of this dust settles on the Caribbean islands and the coasts of Central and South America. Some settles in Europe. Some remains in the atmosphere for years, circling the entire planet multiple times. This dust is a critical source of nutrients for some ecosystems. Phosphorus and iron in Saharan dust provide essential nutrients for tropical soils and for ocean phytoplankton. Some research suggests that Saharan dust provides a significant portion of the phosphorus needed to sustain the productivity of Caribbean ecosystems. Dust particles also serve as condensation nuclei for clouds, as discussed earlier. So the dust from one region can influence cloud formation and precipitation patterns in other regions. The dust particles that serve as the nucleus for a raindrop that falls in Brazil might have originated in the Sahara, thousands of kilometers away. Pollution particles also travel vast distances in clouds. Industrial pollution from Asia travels across the Pacific and reaches North America. Smoke from forest fires in Southeast Asia travels across the Indian Ocean and affects air quality in India and the Middle East. These dust and pollution particles, traveling in clouds, connect distant regions and demonstrate the global nature of atmospheric processes. This intercontinental transport of dust and particles demonstrates an important principle. There is no away in Earth's systems. Particles released in one region inevitably end up somewhere else. They travel through the atmosphere in clouds. They fall with rain. They settle out, but they don't disappear. Understanding how materials cycle through the atmosphere via clouds is essential for understanding global environmental change. Clouds contain salt crystals from ocean spray that influence their properties. When waves break on the ocean's surface, they spray water droplets into the air. These droplets contain salt. Some of the water evaporates, leaving behind salt crystals. These salt crystals are carried into the atmosphere, where they can travel enormous distances. These salt crystals are excellent condensation nuclei. They attract water molecules readily, allowing clouds to form more easily in air that might otherwise be too dry to support clouds. This means that maritime regions with abundant salt crystal condensation nuclei often have more and more persistent clouds than continental regions. The presence of salt also affects cloud droplet size and cloud optical properties. Clouds rich in salt nuclei tend to have more numerous but smaller droplets. Clouds with fewer nuclei tend to have fewer but larger droplets. These differences in cloud microstructure affect how the cloud scatters light, how bright it appears, and how it reflects and absorbs solar radiation. Interestingly, this relationship between aerosol particles and clouds creates a potential climate feedback. If pollution increases the concentration of aerosol particles, it can increase cloud droplet concentration. More numerous droplets in a cloud makes the cloud brighter. It reflects more light. This increased reflectivity could provide cooling, but it also changes the cloud's microphysical properties in ways that can suppress precipitation, causing the cloud to live longer and persist in one location. These effects all interact in complex ways. Clouds interact with human pollution in unexpected ways. As human industry has grown, the amount of aerosol particles in the atmosphere has increased. These particles, sulfates from burning coal, black carbon from diesel engines, organic compounds from manufacturing, and solvents all serve as condensation nuclei. In some cases, this has increased cloud formation. Regions downwind of major industrial areas sometimes have more clouds than they would naturally have, because the increased aerosol loading provides more condensation nuclei. This phenomenon is sometimes called the urban cloud effect, or aerosol indirect effect. But the relationship is complex. More aerosols mean more cloud droplets, but smaller average droplet size. Clouds with numerous small droplets have different precipitation properties than clouds with fewer, larger droplets. In particular, clouds with numerous small droplets are less efficient at producing rain because the droplets must collide and merge for raindrops to form. More, smaller droplets means more collisions would be needed. This is why some regions with high pollution have become drier, despite having more clouds. The clouds are less efficient at producing rain, so precipitation decreases. Some scientists hypothesize that pollution-induced changes in cloud properties may have contributed to droughts in some regions. This unintended consequence of pollution demonstrates the complex interconnections in Earth's systems. Actions taken to satisfy immediate human needs, burning coal for energy, manufacturing goods have side effects on cloud formation and precipitation that feed back to affect human welfare in unpredictable ways. Contrails are artificial clouds formed by aircraft engines. When a jet airplane flies through the atmosphere, its engines emit hot exhaust containing water vapor. As this hot exhaust exits the engine and mixes with the cold ambient air at high altitude, the water vapor rapidly cools and condenses into droplets, forming a visible trail behind the aircraft. This is a contrail, a condensation trail. Contrails only form under certain atmospheric conditions. The air must be cold enough and moist enough that the mixing of hot exhaust with ambient air produces saturation. If the air is too dry, contrails don't form. The water vapor evaporates into the ambient air without condensing. If the air is too warm, contrails also don't form. On many days, airplanes fly without leaving visible contrails. But on other days, contrails persist for hours, spreading out as they drift with the wind, creating visible lines across the sky. On particularly moist days, a sky full of aircraft can become covered with a network of contrails, creating a nearly complete cloud cover within hours. Contrails are artificial clouds, made not from natural atmospheric processes, but from the interaction of human technology with the atmosphere. They contain the same water droplets and ice crystals as natural clouds, and they have similar optical and radiative properties. But because they form at specific altitudes and locations determined by aircraft flight paths, their distribution is entirely different from natural clouds. Some research suggests that contrails and the cirrus clouds they create or enhance have measurable effects on Earth's radiation balance. Some studies have found that daytime satellite observations show reduced solar radiation reaching the surface in areas covered by contrails, indicating cooling, but nighttime observations sometimes show increased downwelling infrared radiation, indicating warming. The net effect depends on complex factors and remains an area of active research. The existence of contrails demonstrates how profoundly human activity now affects even something as fundamental as cloud formation. Every airplane that flies creates clouds, artificial clouds that persist for hours and can influence the local radiation balance. If air traffic were to suddenly cease, as happened for a brief period after the 11th of September 2001 terrorist attacks, the absence of contrails could be measured in atmospheric and surface observations. Clouds have been the subjects of extensive scientific study and computer modeling. Understanding clouds, how they form, how they develop, what properties they have, how they affect climate, has become a major focus of atmospheric science. Climate scientists recognize that clouds are one of the largest sources of uncertainty in climate change projections. To understand clouds better, scientists have developed sophisticated computer models that simulate cloud formation and development. These models represent air parcels rising and cooling, water vapor condensing around nuclei, droplets coalescing into raindrops. They simulate the complex thermodynamic and dynamical processes occurring within clouds. But modeling clouds is extraordinarily difficult. Clouds form and evolve on scales from micrometers, the size of cloud droplets, to kilometers, the size of storm systems. Simulating all these scales simultaneously in a computer model is computationally impossible. So scientists use simplifications and parameterizations equations that approximate what's happening without simulating every detail. These approximations introduce uncertainty. Different models make different assumptions about cloud formation, about droplet size distributions, about precipitation efficiency. These different assumptions lead to different predictions of how clouds might change as the climate warms. Despite the computational challenges, cloud modeling has made tremendous progress. Modern climate models can simulate reasonably realistic cloud patterns. They can reproduce seasonal variations in cloud coverage. They can simulate the formation and dissipation of weather systems. The models are far from perfect, but they're sophisticated enough to be useful for understanding how climate might change. Scientists have also developed sophisticated instruments for observing clouds. Satellites equipped with radiometers measure the brightness of clouds, inferring their properties from the radiation they emit and reflect. Cloud-resolving radar can penetrate clouds and measure the distribution of droplet and ice crystal sizes. Aircraft equipped with instruments can fly through clouds and directly measure their properties. These observations have revealed details of cloud structure that were surprising and unexpected. The assumption used to be that clouds were relatively uniform structures, but observations revealed that clouds are actually highly heterogeneous, with regions of very dense droplets adjacent to clear air, with complex three-dimensional structure, with vigorous mixing at their boundaries. The Titanic's sinking may have been influenced by unusual cloud and sea conditions. On the night of April 14 to 15, 1912, the RMS Titanic struck an iceberg in the North Atlantic and sank, killing more than 1,500 people. The exact causes of the accident involved multiple factors, but atmospheric conditions, particularly cloud cover and visibility, may have played a role. The night was particularly clear and dark, with minimal moonlight. Many survivors reported that they couldn't see the iceberg until it was very close. The combination of a clear, moonless night and absence of clouds created poor visibility despite the darkness. Had there been clouds, they might have reflected moonlight or the faint light of stars, providing some illumination of the iceberg. Had there been fog, it would have forced the ship to slow down. The sea conditions that night were also unusual. The water was extraordinarily calm, like glass. Normally, icebergs are surrounded by churning waves that create a white, foaming wake around them. This wake is visible from great distances and serves as a warning. But on this calm night, the iceberg made no such wake. It was invisible against the dark water until it was far too close to avoid. This convergence of unusual conditions, clear skies, lack of moonlight, unusually calm seas, created a perfect storm of poor visibility. The ship's lookouts were looking for the characteristic white foam of breaking waves against the iceberg. They were watching for the white foam that would indicate the presence of ice, but there was no white foam. The calm seas removed the usual warning signs. The story of the Titanic's sinking illustrates how profoundly clouds and atmospheric conditions affect human endeavors. Ships depend on visibility to navigate safely. Airplanes depend on ceiling heights and visibility to operate safely. Entire economic and safety systems are built on assumptions about the probability of particular atmospheric conditions. When those conditions deviate significantly from expectations, tragedy can result. Clouds shape human settlement patterns and culture. Throughout history, humans have settled in locations partly determined by cloud and precipitation patterns. Civilizations developed in regions with reliable precipitation patterns that allowed agriculture to flourish. The Nile River Valley, supported by monsoon rains that form clouds over the Indian Ocean, supported one of history's greatest civilizations. Civilizations in East Asia developed in regions of monsoon precipitation, where clouds reliably bring rain in summer months, allowing rice cultivation. Conversely, regions with persistent cloud cover, but little precipitation, like some fog-shrouded coastal deserts, remained sparsely populated for centuries. The Atacama Desert in South America and the Namib Desert in Africa both have frequent fog and clouds, but very little rainfall. The moisture in the clouds cannot reach the ground as precipitation. These regions remained nearly uninhabited until modern technology made settlement possible. Religious traditions have incorporated clouds into their understanding of the divine. Many religious texts describe clouds as the dwelling place of gods, or as vehicles through which the divine communicates with humans. In the Old Testament, God's presence is often indicated by a cloud. In Hindu traditions, clouds are associated with the god Indra. In Japanese Shinto, clouds are seen as manifestations of natural spirits. These religious perspectives reveal how profoundly clouds have captured human imagination and spiritual yearning. Festivals and celebrations often incorporate cloud-related weather phenomena. Monsoon festivals celebrate the arrival of monsoon rains and the clouds that bring them. Winter festivals in regions that experience snow celebrate the formation and falling of snow from clouds. Harvest festivals often include rituals requesting favorable cloud cover and rain for crops. Across cultures, humans have ritualized their relationship with clouds, acknowledging their dependence on cloud-produced precipitation. Clouds create optical phenomena that are beautiful and sometimes mysterious. When clouds interact with sunlight in particular ways, optical phenomena emerge. A corona is a set of colored rings surrounding the sun or moon, created by diffraction of light by water droplets in a cloud. A halo is a ring of light surrounding the sun or moon, created by refraction through ice crystals. A glory is a set of colored rings around the antisolar point, the point directly opposite the sun, visible sometimes from airplanes flying above clouds. Pillar light, also called light pillars or light columns, forms when light reflects off ice crystals in clouds or fog. If there's a light source below the sun, the moon, or even city lights, the light reflects upward through ice crystals, creating a vertical column of light extending upward. These pillars can extend for many kilometers and are among the most beautiful optical phenomena in the sky. Atmosphere. Sundogs are patches of bright light that appear on either side of the sun, particularly when there's a halo. Sundogs form through the refraction of sunlight through ice crystals in cirrus clouds. The position of the sundog depends on the angle at which sunlight is refracted, which depends on the angle of the ice crystals. A crepuscular ray, also called a sun ray or God ray, is a band of light that appears to shine down through clouds. These rays form when clouds partially block sunlight, and the unblocked sunlight creates bright beams between the clouds. The rays aren't actually sunlight traveling downward at an angle, though they appear that way. They're actually approximately parallel rays of light, but atmospheric perspective makes them appear to converge. Still, their appearance is striking and beautiful. These optical phenomena have cultural and religious significance. A sundog has been interpreted as a good or bad omen in different cultures. A pillar of light has been seen as a divine manifestation. These beautiful optical effects, created by the interaction of sunlight with clouds, have inspired religious belief and artistic creation throughout history. Clouds play a role in the formation of severe weather and climate phenomena. The conditions that create clouds also create severe weather. Thunderstorms require rising air, moisture, and instability, the same conditions that create clouds in general, but with more extreme versions of these conditions. The updrafts in a thunderstorm are more vigorous, the clouds taller, the precipitation more intense, the dynamics more violent. Hurricane formation depends critically on clouds. A hurricane is in many ways a giant rotating cloud system, powered by the latent heat released as water vapor condenses into clouds. The warm, moist air from the tropical ocean surface rises, forms towering cumulonimbus clouds, releases latent heat, and creates pressure differences that drive the rotating motion. The hurricane is a cloud-powered heat engine, converting the energy stored in water vapor into kinetic energy in wind. Tornadoes can form where conditions create the strongest rotation. Under particular conditions, the wind shear in the atmosphere creates rotation in horizontal bands of air. Updrafts in a thunderstorm tilt this rotation into the vertical, creating a rotating column of air. If this rotating column extends downward and touches the ground, it becomes a tornado. The tornado is still connected to the cloud above, still drawing energy from the cloud system. On longer timescales, cloud patterns affect climate directly. The distribution of clouds at different altitudes affects the radiative balance differently. Clouds also affect atmospheric circulation patterns, the large-scale winds that drive weather systems. A persistent pattern of clouds in particular locations can reinforce itself, leading to prolonged weather patterns. A very rainy region stays rainy, partly because the moisture-laden air creates clouds that produce more rain, which creates more moisture, which creates more clouds. This is a positive feedback loop involving clouds. Clouds have inspired artists and writers throughout history. Beyond the scientific fascination with clouds, they have inspired artistic and literary pursuits. Claude Monet, the famous Impressionist painter, created a series of paintings of haystacks under different lighting and weather conditions. Each painting shows the same haystack, but with dramatically different cloud cover and lighting, creating entirely different moods and impressions. The paintings reveal how dependent our perception of landscapes is on atmospheric conditions, on clouds, on light. Joseph Turner, another painter, was known for dramatic, moody landscapes dominated by turbulent skies. His paintings often show clouds towering, churning, creating an almost apocalyptic atmosphere. Turner's clouds aren't mere background, but the central subject, the emotional core of his paintings. Writers have used clouds as metaphors and symbols. In poetry, clouds often represent transience, the temporary nature of all things. A cloud drifts by, changes shape, and disappears. This impermanence is used to represent the fleeting nature of life, beauty, love, and all human endeavors. In other contexts, clouds represent obscurity and confusion, the clouding of judgment, the clouding of understanding. In the Romantic literature of the 19th century, clouds took on particular significance. Romanticism emphasized emotion, nature, and individual experience. Clouds, with their constant transformation, their beauty, their connection to both weather and emotion, became emblems of romantic sensibility. Writers like Shelley and Wordsworth wrote extensively about clouds, using them to explore themes of change, emotion, and humanity's relationship to nature. Modern and contemporary poets continue this tradition. The transience of clouds, their constant transformation, their transparency and opacity, their movement with winds, they cannot control these qualities, make clouds apt metaphors for contemporary human experience, for the difficulty of grasping or holding on to anything stable in a constantly changing world. Clouds affect sleep and wakefulness through light levels. Cloud cover affects the amount of light reaching Earth's surface, and this affects human sleep and wakefulness. On clear nights with a full moon, the light is bright enough to read by. On cloudy nights, even with a full moon, the light is minimal. This variation in light levels affects the circadian rhythms that regulate sleep. Humans evolved to be active during daylight and to sleep during darkness. The circadian rhythm, the internal clock that regulates sleep-wake cycles and hormone production, is fundamentally driven by light exposure. When cloud cover reduces light levels, it can affect sleep, timing, and quality. For shift workers and people in northern latitudes experiencing polar nights or polar days, cloud cover adds another layer of complexity. On days when the sun doesn't rise above the horizon for weeks, cloud cover makes no difference. There's still no meaningful daylight. But on days when twilight provides dim light, cloud cover becomes significant. A cloudy day during polar twilight might provide enough light for the circadian system to respond, while a cloudy night might be completely dark. Research has shown that people in regions with persistent cloud cover sometimes experience seasonal variations in mood and well-being. Seasonal affective disorder depression that occurs during seasons with reduced light exposure is more common in cloudy regions. The reduced light from persistent cloud cover means less light exposure, which can trigger depression in susceptible individuals. Conversely, the predictable return of clouds after a period of clear weather can provide psychological comfort. The first rainy day after weeks of drought can feel like a relief, a breaking of tension. The clouds that bring the rain are visible, present, and represent the arrival of something desired. Clouds regulate temperature on daily timescales. In addition to their effects on long-term climate, clouds have immediate effects on temperature from day to day. A clear day warms up significantly. Sunlight reaches the surface unobstructed and heats it directly. A cloudy day stays cooler. The clouds reflect and scatter much of the sunlight before it reaches the ground. At night, the pattern reverses. A clear night cools significantly. Heat radiates from the surface to space without being absorbed by clouds or greenhouse gases. A cloudy night stays warmer. The clouds trap the outgoing radiation and re-radiate it downward, keeping the surface temperature higher. This is why deserts, which have clear skies most of the time, experience such large temperature swings between day and night. During the day, without clouds to follow, block the sun, temperatures soar. At night, without clouds to trap the heat, temperatures plummet. A place that's extremely hot during the day can be bitterly cold at night. This extreme range makes life difficult and has shaped the adaptations of desert organisms. In contrast, tropical regions near oceans often have persistent cloud cover. These regions have less temperature variation between day and night because clouds moderate the extremes. The heat during the day is somewhat blocked by clouds, and the heat at night is partially trapped by clouds. This moderation of temperature extremes, this smoothing out of the daily temperature cycle, affects everything from human comfort to ecosystem function. The daily temperature cycle affects which organisms can live in a region, when they're active, when they breed, when they migrate. Clouds, by moderating this daily cycle, affect the entire ecology of a region. Clouds have been the subject of folklore and weather wisdom for millennia. Long before meteorology became a science, humans observed clouds and developed folk wisdom about what they indicated. Different types of clouds became associated with particular weather outcomes. Certain cloud formations were seen as omens of rain, others as signs of fair weather, others as harbingers of severe weather. Farmers particularly developed sophisticated knowledge of cloud interpretation. They needed to know when to plant, when to irrigate, when to harvest. Accurate weather prediction based on cloud observation could mean the difference between prosperity and ruin. A farmer who could correctly predict a coming drought might prepare his fields and save his crops. A farmer who misinterpreted the clouds might plant crops that would fail without rain. This folk wisdom was encoded in rhymes and sayings that made it easy to remember. Mares' tails and mackerel scales make tall ships take in sails. A rhyme about wispy clouds, which might indicate wind changes, and patterned, Clouds, which might indicate instability. A red sky at night is a sailor's delight. A red sky at morning. Sailors take warning. Observations about how light reflects off clouds, with the morning red sky indicating that a storm system has passed overnight and is moving away, so caution is warranted. These folk sayings weren't perfect. Weather is too complex to reduce to simple rhymes. But they represented real patterns and encoded genuine meteorological knowledge. They were heuristics, rules of thumb that worked often enough to be useful and remembered. Clouds create a sense of wonder and inspire contemplation. Beyond their scientific, artistic, and practical importance, clouds inspire simple wonder and contemplation. There is something about watching clouds that slows the mind, that invites reflection. The gentle motion of clouds across the sky, their transformation of shape, their play of light and shadow. These things have a meditative quality. People lie on their backs in fields and watch clouds drift overhead, finding shapes in them, letting their minds wander. This is a nearly universal experience, something children do naturally, and that adults often reclaim as a form of relaxation and stress relief. There's something about the clouds' constant transformation, their refusal to hold a single shape, that encourages the mind to release its grip on fixed ideas and expectations. Clouds are ephemeral in a way that touches something in human consciousness. They form, they change, they dissipate. They last minutes or hours or days, but not years. They're temporary by nature. This transience resonates with human awareness of our own transience, of the temporary nature of all experience. Watching clouds can produce a state of calm alertness. The mind is engaged, but not in a focused, goal-oriented way. The observer is present, aware, noticing the details of shape and light and motion, but not trying to accomplish anything. This state is similar to what contemplative practices try to induce: a calm, clear awareness without grasping or judgment. Clouds connect us to planetary processes larger than ourselves. As you lie here, allowing your breathing to deepen and your body to relax, consider the clouds above you, if you're outside, or imagine them if you're inside. These clouds are manifestations of processes that are far larger than any single human. They represent energy flows from the sun, the circulation of the atmosphere, the cycling of water through the planetary system. Each cloud is composed of particles of dust and salt that may have traveled thousands of kilometers. Each cloud contains water that fell as rain in some distant place, evaporated into the atmosphere, and is now condensing into visible form. Each cloud is a temporary gathering of matter and energy, stable only for a few hours before transforming into something else. You yourself are part of this system. The water in your body came from clouds. The oxygen you breathe was released by plants that depend on clouds for moisture. The weather you experience, the seasons you live through, the climate of the place where you dwell, all are fundamentally shaped by clouds. When you observe clouds, you're not just looking at water vapor and droplets. You're observing the physical manifestation of planetary processes. You're seeing the circulation of matter and energy that sustains all life. You're witnessing the dynamics of a living, breathing planet. Contrails are artificial clouds formed by aircraft engines. When a jet airplane flies through the atmosphere, its engines emit hot exhaust containing water vapor. As this hot exhaust exits the engine and mixes with the cold ambient air at high altitude, the water vapor rapidly cools and condenses into droplets, forming a visible trail behind the aircraft. This is a contrail, a condensation trail. Contrails only form under certain atmospheric conditions. The air must be cold enough and moist enough that the mixing of hot exhaust with ambient air produces saturation. If the air is too dry, contrails don't form. The water vapor evaporates into the ambient air without condensing. If the air is too warm, contrails also don't form. On many days, airplanes fly without leaving visible contrails. But on other days, contrails persist for hours, spreading out as they drift with the wind, creating visible lines across the sky. On particularly moist days, a sky full of aircraft can become covered with a network of contrails, creating a nearly complete cloud cover within hours. Contrails are artificial clouds, made not from natural atmospheric processes, but from the interaction of human technology with the atmosphere. They contain the same water droplets and ice crystals as natural clouds, and they have similar optical and radiative properties. But because they form at specific altitudes and locations determined by aircraft flight paths, their distribution is entirely different from natural clouds. Some research suggests that contrails and the cirrus clouds they create or enhance have measurable effects on Earth's radiation balance. Some studies have found that daytime satellite observations show reduced solar radiation reaching the surface in areas covered by contrails, indicating cooling. But nighttime observations sometimes show increased downwelling infrared radiation, indicating warming. The net effect depends on complex factors and remains an area of active research. The existence of contrails demonstrates how profoundly human activity now affects even something as fundamental as cloud formation. Every airplane that flies creates clouds, artificial clouds that persist for hours and can influence the local radiation balance. If air traffic were to suddenly cease, as happened for a brief period after the 11th of September 2001 terrorist attacks, the absence of contrails could be measured in atmospheric and surface observations. Clouds have been the subjects of extensive scientific study and computer modeling. Understanding clouds, how they form, how they develop, what properties they have, how they affect climate, has become a major focus of atmospheric science. Climate scientists recognize that clouds are one of the largest sources of uncertainty in climate change projections. To understand clouds better, scientists have developed sophisticated computer models that simulate cloud formation and development. These models represent air parcels rising and cooling, water vapor condensing around nuclei, droplets coalescing into raindrops. They simulate the complex thermodynamic and dynamical processes occurring within clouds. But modeling clouds is extraordinarily difficult. Clouds form and evolve on scales, from micrometers, the size of cloud droplets, to kilometers, the size of storm systems. Simulating all these scales simultaneously in a computer model is computationally impossible. So scientists use simplifications and parameterizations, equations that approximate what's happening without simulating every detail. These approximations introduce uncertainty. Different models make different assumptions about cloud formation, about droplet size distributions, about precipitation efficiency. These different assumptions lead to different predictions of how clouds might change as the climate warms. Despite the computational challenges, cloud modeling has made tremendous progress. Modern climate models can simulate reasonably realistic cloud patterns. They can reproduce seasonal variations in cloud coverage. They can simulate the formation and dissipation of weather systems. The models are far from perfect, but they're sophisticated enough to be useful for understanding how climate might change. Scientists have also developed sophisticated instruments for observing clouds. Satellites equipped with radiometers measure the brightness of clouds, inferring their properties from the radiation they emit and reflect. Cloud-resolving radar can penetrate clouds and measure the distribution of droplet and ice crystal sizes. Aircraft equipped with instruments can fly through clouds and directly measure their properties. These observations have revealed details of cloud structure that were surprising and unexpected. The assumption used to be that clouds were relatively uniform structures, But observations revealed that clouds are actually highly heterogeneous, with regions of very dense droplets adjacent to clear air, with complex three-dimensional structure, with vigorous mixing at their boundaries. Let yourself drift with the clouds into sleep and rest. As you continue to breathe slowly and deeply, imagine yourself floating among the clouds. Feel yourself rising gently, the temperature cooling as you ascend. Around you, the clouds envelope you in their soft, gray-white embrace. You are no longer looking at clouds from below, but moving among them, through them, becoming part of them. The air is cool and moist. The light is diffuse and gentle, without harsh shadows. There is a sense of peace, of being held by something vast and gentle. The world below fades into obscurity. There is nothing but the soft, featureless expanse of the cloud around you. Your thoughts, like the clouds, begin to drift and transform. A worry becomes a different shape and moves away. A memory becomes vapor and dissolves into the surrounding mist. You are held in a state between waking and sleeping, between thought and non-thought, between the particular and the vast. The clouds continue their gentle motion. They have no destination, no goal, no particular purpose except to exist and to transform. In their purposeless drifting, they teach a lesson about release, about letting go, about the peace that comes from ceasing to grasp or strive. As your breathing becomes slower and deeper, as your thoughts become fewer and gentler, let the clouds carry you towards sleep. Let the soft, diffuse light of the cloud envelope you. Let the cool, moist air surround you, calm and peaceful and eternal. The clouds have been here long before you were born. They will continue long after you are gone. In their temporary gathering and dissolution, they teach us that nothing is permanent, that change is the only constant, that peace comes from accepting the nature of reality rather than resisting it. Feel your body growing heavier, sinking deeper into the support beneath you. Feel your breathing becoming more automatic, requiring less conscious attention. Feel your awareness becoming softer, less focused, more diffuse like the light through clouds. The clouds drift on, carrying you with them, carrying you toward rest and sleep, and the dreams that live in the space between waking and sleeping. Let yourself go. Let the clouds have you. Trust in their gentle motion, their patient transformation, their ancient wisdom about the nature of change and impermanence. And so, dear listener, our journey through the science and poetry of clouds comes to a close. We have examined how they form and how they change. We have explored how they affect weather and climate, how they have shaped human history and inspired human creativity. We have seen how they connect us to planetary processes larger than ourselves, how they embody principles of impermanence and transformation. The clouds in the sky above you, whether you can see them or imagine them, are still doing their work. They are still circulating water through the planetary system. They are still exchanging energy between surface and space. They are still transforming according to the laws of physics and thermodynamics. They are still beautiful, still worthy of wonder, still inviting us to look upward and remember our place in a living, breathing world. As you rest now, knowing that the clouds continue their eternal work above you, let your mind release its cares and concerns. Let your body find complete relaxation. Let yourself sink into sleep, into the realm of dreams where clouds take forms beyond the physical, where the imagination is free to soar and create without the constraints of physics. The clouds keep watch. The clouds continue their cycles. The clouds will be here tomorrow, transformed but still themselves, still beautiful, still mysterious, still teaching their patient lessons about the nature of impermanence and change. Good night, and may your rest be as peaceful as the clouds drifting through the endless sky.